Okay, good morning class. So we're still busy with the topic on of probability. We are coming to a close with regards to this topic. Yesterday did we speak about the two-way table for independent and dependent events? No, we haven't done anything there. Okay. So yesterday we spoke about the tree diagram. Not so. Then you had homework on it. Is that correct? Right. Was there any problems with the homework? A lot. Okay, no problem. It's okay. Which exercise was it? 12.14. Any problems with 12.14? So the problem is at 12.15. 12.5 I mean. Is that where the issue is, no? 12.5. Any problems with number 1? Huh? Yes. Number 3? Number 5? Yes. So it's 1 and 5. 7? 9? 9 the issue? No. So it's just 1 and 5. Why are you late?
Toilet duty.
Toilet duty? No. Now you missed out on the maths lesson. The toilet. Okay, shh. Which page was this on? Yes? 441. 114. 414. 414. Okay. So in question 12.5, in exercise 12.5, we are told in this exercise you can use a tree diagram when necessary, but you may prefer to do the problem without the help of tree diagram. Okay? So if you decide not to use a tree diagram, no problem. Okay? Okay. So a bag contains 12 chocolates and 8 toffees. Then we are told that Kathy and Thembi each takes one of the sweets from the bag at random. Calculate that they both choose toffee. So if you look at this here, of course, the tree diagram is going to be the better option to go. Not so. So, let's say Kathy throws on the first event. What options does Kathy have? So you can either choose a chocolate sweet, or chocolate or a toffee. There are 12 chocolate sweets and 8 toffees. So how many sweets are there altogether? 20. So there's 12 out of 20, she has the probability, and 8 out of 20 toffees. That's the probability. Together this adds up to? To what? 1. Not so. Now the second person, Thembi, if she throws the second account, if Kathy has drawn a chocolate sweet on the first draw. What is the probability for Tembi to draw a chocolate sweet? 11 out of 9. Remember, once Kathy takes out the first chocolate sweet, does she put it back? No. So out of the 20 sweets that's left in the bag or as an option, there's only 11 chocolate sweets left out of a total of 19 chocolate sweets. 19 sweets in total. How many toffee sweets are left in the bowl or in the bag or to choose from? 8. 8 out of how many sweets? 19. Yes. Think about it. If you take a sweet out of a bowl and I move to the next person, do I expect you to put it back? No. So why are you expecting that to have they tell you to? It's yeah, if it was balls or discs or whatever, then they will tell you it will be replaced. But if you think about it in reality, if you give something, you must now. Don't take it. But okay, hopefully they'll tell us if it's replaced or not. Clearly it's not replaced. Okay. What if Kathy throws a toffee sweet in the first account? Then what is Tembi's probability then? 7 out of 19 for the toffees, yes. And for the chocolate? 12 out of 19. Is there any confusion here? What is the confusion? Yes.
So why is it going 12 out of 19?
Because if she has drawn a toffee sweet, we still have 12 chocolate sweets in the bag. That's why it's 12 out of 19. Yes, Michael?
And then it's 19 because she took one toffee.
Yeah. She took one toffee out of from the options. Any other confusion? So what are my outcomes? It can be chocolate, 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 toffee, toffee, chocolate, toffee, toffee. Not so. So let's look at A. They both chose toffees. So it's this one here. That's the branches I would follow. Not so. So both coming in at toffee. The probability of TT is going to give you 8 over 20 times 7 over 90. It gives us? Sorry? 14 over 95. Let's look at B. B says at least one of them are chocolates. So what are my options here? Chocolate, chocolate. Chocolate, toffee. Toffee, chocolate. Not so? So if I do that calculation, it's going to be 12 over 20 times 11 over 19 plus. 12 over 20 times 8 over 19 plus. 8 over 20 times 19, well, 12 over 19. Not so? I add them all together. Or what could I have used? I can use the complementary rule. Because this is the only one that's not accounted for. Not so? All these probabilities will always add up to? What will that always add up to? 1. Not so? So I can then just say it's 1 minus the probability of toffees. Okay? I've calculated that already. So it's 1 minus 14 over 95. That gives us an answer of 81 over 95. Is that correct? Any confusion here? Any confusion, people? Who got number 3 wrong? I must do all the odd numbers basically. I'm not going to do tomorrow any even numbers, no? I'll do all the odd numbers today. The even numbers is for homework, okay? After this explanation, you should be able to answer all these questions pertaining the tree diagram. It's very important. This also gets tested in grade 12. Okay, so it's important to understand the concept that's being tested here or taught. Right, number 3. In number 3, a bag contains 5 red discs, 7 blue discs, and 3 green discs. So how many discs are there in total? 5, 7 is 12, 3 is going to give you 15. So if you draw a tree for the first account, it can either be red, blue, or green. Since it's 5 red, 5 out of 15, 3 green, 7 blue, 7 out of 15, and 3 green, 3 out of 15. You all agree with that? So irrespective if the disc is being replaced or not replaced, the first event remains the same. Not so? No. The 2 discs are drawn at random from the bag. So, do you think it's going to be replaced yet? No. So I'm going to treat that as not being replaced. I think when they will specify if it's being replaced. I think that is fair. Yeah? They will tell you it's being replaced. So in other words, if they draw a red on the first account, then you're going to get red. Okay, I'm just going to draw this a bit bigger with a lower. So, if the person draws red on the first account, the options are red, blue and green again. How many discs are in the bag then? 14. So, if it's red, how many reds do we have? 4 out of 14. Blue, 7 out of 14. Green, 3 out of 14. Does it make sense? Right, let's look here. It's going to be red, blue, green. If the first disc removed was blue, how many red do we have? Still 5 out of 14. Blue, 6 out of 14. Remember, I took 1 out here. Okay? And green, 3 out of 14. What if the first row was green? How many green do we have? 2 out of 14. Blue? It remains 7 out of 14. Red? 5 out of 14. You will agree with that? What are my outcomes? Red, blue? Red, green? Red, red. Not so? Then blue, red, blue, 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 green. Green, red, green, blue, green, green. You all understand? Any confusion here? No confusion. Both discs are red. Both discs are red. The only option I have is that one there. That's all. So both are red. The probability of RR is going to be 5 over 15 multiplied by 4 over 14. Gives us 2 over 21. Any confusion there? No? Let's look at B. Both this are the same color. So if both this are the same color, it's going to be the probability of red, which I have calculated. So that's an option. Both blues and both greens. Not so. That's going to be the probability of both blue plus the probability of both green. Both red is it's 2 over 21. I'm not going to rewrite that probability again there. Plus both blue. So that branch I'm following. So it's going to be 7 out of 15 times 6 out of 14 plus 3 out of 15 and 2 out of 14. Okay, that gives us what? 34? 105. Any confusion there? You all understand? Right. Let's look at C. If I'm looking at C, at least one disc is green. Will I consider R? No? No? Yes. This one? No? No? Yes. This one? Yes. 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 Did you see that, people? So I can say it's going to be 5 out of 15 times 5 out of 15 times 3 over 14 plus that and that plus that and that. Not so? So instead of working out 1, 2, 3, 4, 5 probabilities, I can just say 1 minus 3 probabilities. Not so? But if you wanted to say 5, no problem.
No.
Yes?
Why would you want this 3 open?
Yeah, because it's actually 4 open.
4, yeah.
4 and 5 is shaded. It's shaded. Okay. It's about the same. 1 minus that is unmarked. The same as the marked values only. Remember why? Because all this adds up to 1. Not so? So I'm just going to write it all out. The probability of both red-green plus probability of blue-green plus the probability of green-red plus the probability of green-blue plus the probability of green-green. So red-green is 5 over 15 times 3 out of 14 plus green-blue, no, blue-green, sorry, I'm looking at blue-green is 7 out of 15 times 3 out of 14 plus 3 out of 15 times 5 out of 14 plus 3 out of 15 times 7 out of 14 plus 3 out of 15 times 2 out of 14. That gives us an answer of what? 13 over 35. Any confusion there, people? Any confusion here? Let's look at number 5. Okay, number 5, we are told that Neil has 8 loose socks in a drawer. 4 are identical black socks, 2 are identical grey socks, and 2 are identical white socks. He has 8 loose socks in the drawer. Right, let's go with that. I might be wrong, it's just check here. No? So if he has 8, so the total will always be 80. Not so? Okay. 4, if it's black, 4 out of 8 is black. 2 out of 8 is grey. And 2 are white. Okay. He puts his hand in a drawer and randomly pulls out 2 socks. So if he pulls out the one, you think he's going to replace the other? No. So if he draws black first, then what's the probability on the second draw? 3 out of 7. Green? 3 out of 7. White? 2 out of 7. Is this a 2 here? So it's going to be 2 out of 7.
Sir,
Yes?
why is it 7 when you pull up 2 socks?
No, you see what happens is he pulls one sock out and then the other. Yeah. So it's blue, green, white. Right, let's go again. We pulls blue on the first row. It's 3 out of 7. There's a probability of the second sock. Okay? Then, this is 2 out of 8, so it's 2 out of 7. Then, 2 out of 7. Again, blue, green, white. If he pulls green first, grey, sorry, not green, grey. It's going to give you 4 out of 7. Then, 1 out of 7. Then, 2 out of 8. 7 is absolutely 2 out of 7. The next one, blue, green, white. It will be 4 out of 7, 2 out of 7, and we pull the white. It's 1 out of 7 socks left. So what are my outcomes? Blue, 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 green, blue, white. Green, blue, green, 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 white. White, blue, white, green, white, white. Okay. First question. Both socks are black. In the first case, both socks are black. So that is following this branch here, not so. So the probability of both black socks has to be 4 out of 8 times 3 out of 7, which is 3 out of 40. Okay. Let's look at B. Both socks are the same color. So both black or both grey or both white. Both black is 3 out of 40. Both grey, following this branch here, is 3 out of 8 times 1 out of 7. No, 2 out of 8. Why am I always saying 3? Handwriting. 2 out of 8. Both white. 2 out of 8 times 1 out of 7. This gives us an answer of 2 out of 7. So the chances of him drawing identical socks is very slim. No? Very small. 2 out of 7 is how much percent? The chance of him drawing a pair of socks of identical colors is less than 30%. Very small. No? Let's look at the next one. You guys getting the idea now? Okay. It's number 7. Okay, number 7. A bag contains 6 red counters and 4 blue counters. How many counters are there in total? 10. It says 6 red and 4 blue. 3 counters are taken from the bag at random. So how many branches are we going to have? This is going to branch off. This is the first counter. This is the second counter. No red. So what is the probability on the first branch? We draw red first. 5 out of 9. And blue? 4 out of 9. We draw blue first. The red would be 6 out of 9 and blue 3 out of 9. You all okay with that? So that's on the second row, the second counter. The third counter, it could be red or blue, red or blue, red or blue, red or blue. So, if you had drawn red, and then red again, what would it be? 4 out of 8. Remember, all of this is going to be over 8 now. Okay. So, there's 8 counters left in the bag. Not so? What to choose from? How many blues would I have at that point? 4. Not so. If I had drawn a red, then a blue, what's the probability of a red again? It's going to be 5 out of 8. Blue? 3 out of 8. You all agree with that? Let's go the other way. We draw blue first, then red. Probability of red again? It's going to be 5 out of 8. Blue? 3 out of 8. If you had drawn blue, what's the probability of a red? 6 out of 8. And blue? 2 out of 8. Does it make sense? What are the outcomes? R. R, B, R. Now R, B, sorry. R, B, R. R, B, B. So yes, that's 4. Then we got the other one, the blue first. So it's blue, R, R. You see, I also do it in order that I don't miss anything. B, B, R. And B, B, B. Those are my 8 outcomes. Okay. So let's answer the first question. The first question says, all the counters are red. So what's the probability that all are red? It's going to be following that branch here, not so? So it's going to be 6 out of 10 times 5 out of 9 times 4 out of 8. That gives us what? Sorry? 1/6. Okay. Let's go with the second one. P. Whoops, D. P. 3 diagrams will make me come one. All 3 counters are blue. Simple. Why is it such an easy sum? All 3 is blue. Okay? So you're following this branch here now. Not so? So that's going to give you 4 out of 10 times 3 out of 9 times 2 out of 8. That gives us 1/30. Let's go with C. At least 2 counters are red. At least 2 counters are red. So, we consider this one? Yes, this one? Yes, this one? Yes, this one? Why not? Are you referring not to that one? Oh, okay. But the next one, yes? The next one? No? Next one? Next one? So, if you're going to look at this here, it's going to be the probability of red, which I do have, plus the probability of R or B, plus the probability of RBR, plus the probability of BRR. Okay? The first probability we have calculated already to be 1 out of 6. Not going to do it again. RR, so it's going to be 6 out of 10 times 4/9. No. RR, 5/9 times B, which is 4/8. Plus probability of RBR. RBR is going to be 6/10 times 4/9 times 5/8. Plus BRR 4/10 times 6/9 times 5/8. So that gives us what? Sorry? 2/3. Any confusion here? No? And then the last one. Only of the counters are, only 2 of the counters are red. So only 2 is going to be that one there, and this one there. Not so? But what have we worked out? We have worked out inclusive of that one. Not so? So in other words, for that account, for D, it's going to be the probability of what we got in C minus this one, which is that value there, 1/6. Not so? So that's going to give you 2/3 minus 1/6. Or you could have said that, plus that, plus that. Should have also given you this answer. Not so? And that's the answer equals half. Okay? Any confusion? No. Is there another one? Number 9. Number 9, we are told that a box of pens contains 3 red pens, 2 black pens, and 1 green pen. You got red, black, green. How many reds you have? 3 out of 6. 2 black, 2 out of 6. Green, 1 out of 6. 2 pens are taken from the box at random. So it's going to be red, blue, green. Red, blue, green. Red, blue, green. We draw red first. It's 2 out of 5. Blue will be 2 out of 5. Green would be 1 out of 5. If I had drawn blue first, red will be 3 out of 5. Blue would be 1 out of 5. Green would be 1 out of 6. 1 out of 5. We'll draw green first. 0 out of 6 for green. 5. Red. 3 out of 5. Green. Blue. 2 out of 5. Outcomes. Red, red. Red, blue. Red, green. Blue, red. Blue, blue. Blue, green. Green, red. Green, blue. Green, green. That's your outcomes. Calculate the probability that both the pens taken from the box are of the same color. So, the same color could be red, red, blue, blue, green, green. That's all. So that would simply be probability of red, red, plus the probability of blue, blue, plus the probability of green, green. So that would be 3 out of 6 times 2 out of 5 plus 2 out of 6 times 2 out of 6 times 1 out of 5. That's the first one I went with. 1 out of 5 plus both green 1 out of 6 times 0 out of 5. Put it in the calculator, you get an answer. Sorry? 4 over 50. Right. This will give you 0 here. No? Why is that 0? There is no way you can pull 2 greens at the same time. Why? Because there's only 1 green in the box. Does it make sense? Oh my word. After 40 minutes, you can't say yes or no. People, 2 white tables for independent and dependent events. Okay. So at this point, we gave you homework. Your homework is going to be the even numbers of that exercise. Okay. I'm looking at the example on page 415. Example on page 415. Okay. So here we are told that 100 people were asked which season they preferred, and the information was entered in the accompanying two-way table. Okay. So you got females, males, like summer, likes winter, and that's the table that they came up. Okay. If you look here, this, if you look at the 30 would represent the people who like summer and being female at the same time. Can you see that? This here is the total number of females. This here is the total number of people who like winter. Not so. This here is what? Total number of males who likes winter. This here, the total number of people here that was surveyed. Does it make sense? No? Right. The question says, determine the following. P stands for probability. Determine the probability that it's female. What's the probability that the person selected at random is female? 50 out of 100. Female? 15. That's your total. 100. 50 out of 100, which is? You all agree with that? Any confusion? B. The probability of male and like winter. The probability of male likes winter is how much? 11. Can you see that? So it's going to be 11 out of. And the last one, the probability of female and like summer. Female like summer. It's going to give you 20 over. That's like winter. My mistake. There. Is that correct? Female and like summer. It's 30. It's 3 out of 10. Okay. All okay with that? Any confusion? No. Okay. It's fairly simple, no? Until you do the homework and you give me a whole list of stuff I must do. Alright, so now we're going to consider whether the season preference depend on gender or not. So if we look at example 2, determining whether events are independent or dependent. If A and B are independent events, then the probability of A and B, that is basically your intersection, where they meet. Like if we look at this here, this is probability of female and like summer. This is and. Not so, that's your intersection. So what they're telling you is that the probability of A intersection B, if A intersection B is equal to the probability of A, which in this case is going to be like summer, times your probability of B, which is female, if you multiply this together and it's equal to the intersection, then events are independent. So write that down. For independent events, the probability of A intersection B is equal to the probability of A times the probability of B. That you must memorize. You're going to use that extensively in this part, in this section, okay, of work. Probability. It's not on your formula sheet. No? So whenever you read the word independent, events are independent, you write this formula down. Or later on when they ask you to prove that events are independent, then we're proving this identity. Okay? It's a very, very important note to make. Highlight it. Right, let's read on what they say. Conversely, if A and B, conversely is the, what is converse? Not attack, is no. It's the reverse of. No? Converse is the reverse of. Conversely, if the probability of A and B is equal to the probability of A times the probability of B, then A and B are independent events. We can use this fact to test whether an event is dependent on another event. Now, for those of you who are confused, when is an event independent? It's when the second row has nothing to do with the first row. Not so? So the 3 diagrams we drew today, all those 3 diagrams, are those dependent events or independent events? Dependent. Why? Because the second row was dependent on the outcome of the first row. Not so? If we look here, if we look back here, all these events here, all this here was dependent on what happened there. If red went first, that is the outcomes. If blue went first, that was the outcomes. Can you see? So these events are dependent. The first or the second event, which is this year, is dependent on the outcome of the first event. You guys understand? So that is when we say something is that is something that is dependent. If we say it's independent, then that is when the disk is being replaced. So it doesn't matter what was drawn on the first event. The second event will still have its own probability. You guys understand? Likewise, if you take a coin, you're flipping a coin, and you're throwing a die. No? If I throw a 1 on the dice, does it better my chance of flipping a heads on the coin? No. So those events are independent. Which means to say that if I do the probability or the independent calculation on flipping a coin, you will see that the events are independent. Okay? Make sense, people? So let's look at the example 2. And example 2 is on page 416. I think the bell's going to ring soon. I just hope you don't get Afrikaans. Oh my. Auntie gaan my 'n pak gee, né? Next year, please don't get Afrikaans after maths. Because there's so much I want to tell you still. Before you write your finals. No, life science is fine. Don't worry. Oh, no. I'm joking. I shouldn't keep you after the class. Unless you guys start coming after school. Yeah, exactly. But anyway, people listen. Listen, now you see this is the reason why I said you like to Afrikaans. Right. 90 people were interviewed on whether they preferred sweet foods or savory. Okay? You guys know what sweet foods are, no? You don't know? Donuts and what else? Cake? Dessert? That's sweet food. Savory? Samosas? Pies? Tarts? That's savory, no? The problem with us is we want both. Yes. Right, people, here we go. 90 people was interviewed. Right, that's a 90. Whether they prefer sweet food or savory. The results were recorded as follows. Determine the following. Probability of male only. 55 out of 90. Gives us what? 11 out of 18. People, probability of savory. 54 out of 90. Which is? Sorry? 3 out of 5. You all agree with that? Probability of male and savory. Male and savory. Is what? 33 out of 90. Which is 11 over 30. Probability of male times the probability of savory. So the probability of male is 55 out of 90 times the probability of savory is 54 out of 90. Somebody work this out? 11 out of 30. E. Now this is the difference between the two. Does the data collected from the survey show that food preference are independent of gender? So now what comes to mind? The probability of savory intersection male. Why am I going with that? Because it's already calculated it. If that is equal to the probability of savory times the probability of male, if that is the case, then the events are independent of each other. If it's not equal, they are dependent. Okay? Or not independent. So this part of the calculation was done already. So the probability of savory intersection male is equal. Male intersection savory is 33 out of 90. Which is 11 out of 30, not so? Which is, so we say since the probability of savory intersection male is equal to the probability of savory times the probability of male. Therefore, events are independent. And this question is synonymous with this two-way or contingency table. Okay. Whenever you see this, rest assured that this question is going to come. Okay. People, for homework, I want you guys to do. Start picking up, Salon. For homework, I want you guys to do, and tomorrow we'll do example 3 as well. Exercise 12.6, the odd numbers, which also wraps up the syllabus for the year. People, enjoy the rest of your day.